Hello, thank you all for watching, and I'd like to give a special shout out to the organizers of the Grads Conference for keeping this going online. My name is Jake Wands. I am a current student in the Materials Science Department, and today I'm going to talk to you about how selenium can passivate defects in cadmium telluride photovoltaics. As the world's demand for energy continues to increase, we need more renewable energy sources to reduce our carbon emissions. And one of the most promising technologies for this are cadmium telluride thin film photovoltaics. And recent analysis has shown that unsubsidized utility scale CdTe is cheaper than gas peaking plants, coal plants, and is now on par or even cheaper than gas combined cycle. And with global PV capacity expected to double by 2024, this is a technology of great interest. The current record efficiency for CdTe is 22.1% set by First Solar, and much of the recent gains are coming from alloying the samples with selenium. Selenium reduces the band gap, which improves the low energy collection and the short circuit current. But despite reducing the band gap, the open circuit voltage doesn't decrease, and there are several theories for why this may be occurring. It has been shown that the minority carrier lifetime is significantly improved with the selenium alloying. And to study this further, a recent Nature paper from Fiducia et al. Showed that the cathode-luminescence intensity increases with selenium concentration. And this indicates that the defects in the material are being passivated by selenium. But this is still pretty recent and further study is needed. We use scanning microwave impedance microscopy, which is an AFM-based technique that uses a 3 GHz microwave signal applied to a special probe tip to measure the dielectric constant and conductivity. In addition, by applying a low-frequency AC bias, as you can see in the chart, we can gain DCdV information. And DCdV is inversely proportional to carrier concentration, meaning that a higher DCdV is a lower carrier concentration. So we measured 3 as-deposited samples with 5, 10, and 25% selenium content. And to compare the 3 samples, we did a line scan across the middle of these images, which you can see in the chart. As the selenium content increases, we see lower DCdV values, and this indicates that the carrier concentration is increasing. And this could be due to the reduced recombination that comes about from passivating defects. To take this further, we varied the AC bias frequency between 2075 and 150 kHz. You can see in the bottom right corner of each image the average DCdV value for that scan. For each frequency, the overall trend remains the same, that the carrier concentration increases with selenium content. But another observation is that as the bias frequency increases, the carrier concentration decreases. And this is due to the carriers not being able to respond to the higher frequency field. But this effect is less severe in the higher selenium samples, which indicates that the mobility of the carriers is greater in those with higher selenium content. And this could be due to the reduced scattering that is caused by the defect passivation. Another observation is that the grain boundaries become much more visible at higher DCdV frequencies. And specifically, the DCdV value is higher in the grain boundary than it is in the surrounding grain interiors. This indicates that the carriers are less mobile in the grain boundaries, which could be expected due to the high density of defects that occurs at these regions. To summarize this work, SMIM was used to measure increased carrier concentration in CdTe films with selenium alloying. This indicates a reduction in recombination due to defect passivation, which agrees with studies from other groups. Higher SMIM bias frequencies suggest improved mobility with selenium, and this could also be due to defect passivation, which reduces scattering in the samples. The bias frequency impacted grain boundaries more than the grain interiors, showing a lower mobility in these regions. And to further study this, the next step is to compare as deposited to cad chloride treated samples. The cad chloride treatment is used in all high-efficiency devices and specifically impacts the grain boundaries. Seeing how the chlorine interacts with selenium will be the topic of future study. Transient photocapacitance and deep-level transient spectroscopy will be used on samples with and without selenium to further characterize defects, and hopefully this will give some more understanding to the mechanism behind the passivation. We would like to acknowledge the Department of Energy for providing funding for this project, as well as the Ferrakides Group at University of South Florida for providing samples. Thank you.